Hi guys, welcome back to my channel. I'm Abhishek Podil. Today I'm going to solve a problem from fluid mechanics. The relative equilibrium subtopic of hydrostatic. And here you can see a question. This is a case of first vortex motion, in which a liquid is contained in a cylinder and it is rotated about any axis. This is the case. Now let's get into the question thoroughly. Here you can see a cylindrical vessel, 20 centimeter in diameter and 30 cm high, contains oil of specific gravity 0.8. The specific gravity is 0.8 here, and it is used to find out the density and the specific weight of the liquid, and which it contains liquid up to a height of 20 centimeter. It is not initially completely filled. So the height is 30 centimeter, and the liquid is contained up to the height that is 20 centimeter. So and question asks you to find the constant rotational velocity omega about the vertical axis. It's shown in the figure. Figure is given. And the next slide I will show you the figure. When the oil is at the verge of spilling over the vessel, it asks you to find out the angular velocity, giving the condition that there is no spilling here, because in the verge of spilling, that means it is not spilled. So that's why this is the case of no spilling case. Just the condition of spilling. That is, I'm going to show you this in the picture, and illustrate using the picture. So let's go to the another slide. Okay, so here the height of the cylinder is 30 centimeter and the diameter of the cylinder is 20 centimeter, and it contains liquid up to a height of 20 centimeter. It's already given the 20 centimeter in the question. Okay, so that's why oil is up to this point. So I will be back to this point again. So for this, this is the case of initially the liquid stays like this before rotation. This is the case of before rotation. So when it rotates about an axis, the axis is in the left side. The axis is not in the middle. So not all the time the axis is in the middle, but in this question the axis is in just the left side. Axis might be right side, axis might be outside the cylinder. The axis can be anywhere. So you have to be aware of this axis, and in this question the axis is in the left side, and if this is the case of the before rotation case. Okay, so before rotation case, so that's why you are going to. So now after rotation, what will happen after rotation? After rotation, the liquid rotates like it is initially in this dash line. Liquid, when it rotates, this is rotating about this axis, so that's why liquid goes toward outward, outward direction, because it is a fluid. Fluid deforms continuously under the action of shear force. Whether the shear force maybe this is a definition, so that's why it undergoes continuous deformation. So that's why it goes up to this point, yes, spilling point. Okay, so spilling point, yes, is over here. And you have to know that from the initial level it goes up to a height y, and this height is same as the drop here. The rise from the initial level, that is y, is same as the drop. That's why I have written here 0.1 meter, and this is a 0.1 meter. So this is the edge of the paraboloid. This is the edge of the paraboloid, just spilling case, because the question has already stated that it is in the verge of spilling. So that's why you have to understand the liquid goes up to this spilling point. Yes, there is no spilling here. So and this yes is a edge of the paraboloid. Okay, and now this O is what? The O is the vortex of the paraboloid. So this is the vortex of the paraboloid, and I have already told you that the vertical distance between the edge and the vortex is called Z. Okay, the elevation Z, and Z is we know what is the formula of the Z to calculate the angular velocity. So that's why you have to understand that in this case the Z is 0.1 meter plus 0.1 meters, because Z is the definition is that this is the vertical distance between the vortex of the and the edge of the paraboloid. Okay, so now let's get into the solution. Here, the given data are over here. The diameter is given, that is 0.2 meter, and the radius is 0.1 meter, and specific gravity is 0.8. And if the specific gravity is given, then you can you can just multiply it by 1000 to get the density. So that's why I have already multiplied it by 1000, that is 0.8 into 1800 kg per meter cube. and specific weight gamma is equal to 0.8 into 9810. If you do that, and you are going to get the specific weight of the liquid. Here, 0.8 into 9810. I have already done this, and you must know this to convert the to get the specific weight and the density. How to get this? Okay. So now let's get into the solution here. So let's get to the solution, and let's write. Okay. Okay, now okay, so now in this case there is no spilling condition, so oil reaches to spilling point after rotation. I have already told you that it goes to the spilling point, and here vortex is O. I have already told you the vortex is O and the edge is S, and the vertical distance between the vortex and edge is called Z. Okay, so you have got the formula of the Z, that is that is omega square R square divided by 2Z. Okay, so you have already you must know this formula. We have derived this formula in the classroom. Okay, so now Z is what? Z is, we have already got Z here. Z is the vertical distance between edge and the vortex of the paraboloid. So that's why here, according to the previous figure, 0.1 plus 0.1, you are going to get the Z is 0.2 meter. Okay, so Z is 0.2 meter. If you substitute Z over here, you are going to get the omega. Okay, so radius is how much? Radius is 0.1 because the diameter is 0.2. So radius is 0.1 by 2 into 9.81. Okay, you are going to do this, and you are going to get the omega. The omega is how much? The omega, you are going to get the omega 19.81 radian per second. Okay, you have got this omega, and this is the angular velocity. The question asks you to get the angular velocity. It's a very easy question, So this question, you have to understand how the liquid behaves when it gets rotated. So that's why this is only the case here. So, and now what will you do to find out the rotational speed in terms of revolution per minute? Okay, their formula, that is omega is equal to 2 pi n by 60. You are going to do this, and you are going to substitute this omega 19.81 here. 19.81 is equal to 2 pi into n divided by 60. And how much would be the n? N would be, how much is the n? N is 189.17 rpm. 189.17 rpm is n. Okay, this is the revolution per minute. So in 1 minute it revolves around this, and this is not in points. You can just round it up. Okay. So this is the question asks you. This is how a question asks you in the examination, the conceptual question from the chapter hydrostatic. And I'm going to give you some homework here, so that you do this homework. And note 1 is a note 1 here. Note 1. So please determine if this is the case. We have done this case because this is no spilling case. So that's why what will happen if determine volume spilled. You determine. This is the homework for you guys. Determine volume spilled. Determine volume spilled if this cylinder is rotated about 200 rpm. Okay, so what will happen if it rotate about 200 rpm? This is the homework for you. 200 and 300 rpm, both two case. Okay, do these two case, and you can just write a comment in the comment section. You can write the answer, and you can post the solution also. No problem, I'll check that one. Okay guys, first case, this case is 189.17 rpm. This is the this is the no spilling case. But when it rotates more than this, 200 rpm, there will be volume spilled. Okay, so you have to calculate the volume spilled. To calculate the volume spilled, you have to find out the initial volume. Calculate the initial volume, because initially the liquid is up to the height 20 centimeter. Okay, so do this first case 1. This is the case 1, case first. Okay, and this is the case second. Okay, so do these two homework for you guys, and you can write the comment in the comment box, and you can post the solution also. Okay, thank you guys. Thank you for watching this video, and I'll be back in taking another video. Thank you guys. Thank you.